So now both my QMM calculation on neutral and anion thymine is done. So this is my output file for the anion. If I open it with Notepad, so it totally took around 1280 steps to get the convergence. And one important thing to notice here is that once I calculate the frequency, is there an imaginary frequency or not, at least I don't see any imaginary frequency, so we are fine. So for the neutral optimization, what we have done, if I show you the neutral input file, instead of starting from the original PDB geometry, we have started from the anion geometry and then optimize it to neutral, just to make convergence a little faster. So if I open the neutral output file, you also see there is no negative frequency. So now we have to do the single point QMM calculation at a larger basis set. So the way we will do it is that we will take the anion input file, maybe it will remain QMMM, only we will remove the term. For the QM, I will use RIBP86 MA def 2Q ZBP, and of course I have to take it anion.pdb. So let me rename it anion.sp, and for the neutral everything will remain same except this will become 0 1 and neutral.pdb. So this I will save as neutral sp.inp. So Orca neutral sp neutral sp.out. So let us make an Excel sheet where you can do the calculation. This is system, anion SP, anion thermochemistry, neutral SP, neutral thermochemistry, maybe I should have given single, anion total, neutral total, this will be my electron affinity. Remember, electron affinity means neutral total minus anion. So electron affinity is always neutral minus anion, and I want it in EV, so this will be 27.12. This is bulk, and this is isolated. So the neutral calculation has been done. Let us do the anion calculation, but before, no, let me do the anion calculation. Anion SP, put anion So now let me put the single point energies. So this is neutral SP, this is the final QMMM. This is anion SP. Now we have to also add the thermochemistry contribution. So this is neutral dot output file. Somewhere below must be the thermochemistry contribution. this is the free energy minus the electronic contribution. So this is what and this is the neutral total. Similarly for the anion, I also need to find out this is the free energy minus the electronic energy contribution. So its adiabatic electron affinity is 0.7340 electron volt. Remember, we have also done the calculation on the isolated. So isolated anion QZVP is done. Let me open the input file. I can make it isol. Somehow I have screwed up the name. It's isolated. I have written isolated neutral. Also the charge and multiplicity will be 0 and 1. I should have saved it to isolated neutral. Let me undo it. Save it and 0 1. It's Orca. This is the isolated anion quadruple zeta single point. can get the thermochemistry contribution from here. This is free energy minus electronic contribution. And the neutral single point energy. This is isolated neutral QZPP. And the thermochemistry correction. So, the electron affinity values at the isolated is much smaller than what you get in the bulk. Although I am calling it bulk, it is actually microsolvent because 10 water molecule. Now, if you want to think why it happens is that because the water molecule can preferentially stabilize the anion than the neutral. So, what happens is that when water molecules are there, then it actually stabilizes the anion more. So, it leads to an increase in the electron affinity. So, whatever behavior you see in the gas phase may be completely different in a solvent phase. In a next weeks, we are going to describe more about the solvent effects. So, one thing we have not described in this class, and unfortunately ORCA does not have it also, but you should know what is called a polarizable embedding. So, what happens in the case of electrostatic embedding is that the QM part gets polarized by the MM, but the MM part does not get back polarized by the QM. That can lead to certain artifacts. So, the next step in increase the level of sophistication is to include the polarizability of MM atoms. In this case, not only the QM region will be polarized by the MM atoms, the QM region can also induce polarization in the MM system. So, both way polarization is there, and different approaches has been developed to model polarization of MM atoms, because remember MM atom does not contain any wave function. So, you cannot polarize the wave function. So, among the most popular methods are charge on a spring model, induced dipole, and the fluctuating models. To obtain the total QMM energy in the polarizable embedding approach, the MM polarization needs to be computed at every step of self-consistent of the QM atom function. So, what happens is that for a certain level of MM polarization, you start with a gas, do the one iteration of the QM, take back the QM region back polarize the MM, and again iterate the MM polarization, and it goes back and forth. So, sometimes they are more difficult to converge, since the polarization is computed in a self-consistent manner as well. The QMM computation can be very cumbersome and demanding. So, most of the cases people try to avoid it, but if you want to get more accurate answers, especially if you are dealing with excited state, ionization or electron attachment, generally the polarizable embedding gives you much better results than the normal QMM approach with electrostatic embedding with non-polarizable force fields. Okay, so, the other homework problem using the additive coupling will be to calculate the vertical electron affinity of GC. So, to optimize the geometry at BP86 def2 SVP, and by taking guanine at the QM region and performing the single point calculation. Now, this time in a different basis. There is a reason why I calculated in a different basis, but you should do the single point calculation in the omega B97X D3 def2 TZVP. And remember, here we are telling to calculate the vertical electron affinity. That means at the QMM calculation, you do not need to optimize both for the neutral and anion, it will be sufficient to calculate the anion only. And the necessary files, the PDB, PSF and the force field files can be find out in this link. So, I hope at the end of this week's lecture, you know a little bit more about multi-layer modeling, you know what is MM, how the molecular mechanic force fields are built, what kind of parameterization are used, what are popular force field, how to do QMM calculation, what are the different kind of embedding, how to select the size of the QM region and how to cross check it and do few calculations on this one. So, doing this QMM calculation actually allows you to do one kind of a solvation effect. You have already seen it where we have surrounded the thiamine molecule by water molecule. So, this is one kind of a solvation. There are other kinds of solvations available where you do not need to do this kind of lengthy optimization, and they are called the implicit solvation that we are going to discuss in the coming week. And of course, we had discussed a little bit about electron affinity. What is left here is the exciting thing which is very close to my heart is molecular excited state. So, in the next week videos, we are going to discuss about molecular excited state. See you next week.